Thanks. I'll begin with a word of prayer. So, dear Heavenly Father, we thank you again for this opportunity we just have to meet together and study your creation. Thank you, Lord, for your grace and mercy to us this day, each day, Lord. We thank you that you loved us even when we don't love you, Lord. We thank you for that. And I just pray that you would just bless this class, help us to glorify you again, Lord, in what we do. In your name I pray, Lord Jesus. Amen. All right, so I'll devote the first 15 minutes or so of class to your homework questions. So have at it. Yes, sir. Yes. So in physics, we have this concept of center of mass. So for a one-dimensional case, you might imagine masses, say m1, m2, da-da-da. Maybe you've got n masses, all right? A bunch of masses. And these are different coordinates. This one's at x1, this one's at x2, this one's at x3, so forth and so on all the way to xn. Now from this, you can of course define the total mass, m, to just be the sum, I equals 1 to n, of m sub I, right? That's the total mass, no surprise there. And then you can even calculate what's called the center of mass for such a distribution. And the center of mass, basically where all of these could be considered, if you could lump these all together and thought of them as just one big particle and sort of neglected the details, you could say that these are at the center of mass, x bar. Now x bar, turns out what you do is you divide by the total mass, and you take the sum of the xi coordinate times the ith mass, I equals 1 to n. This gives you the so-called center of mass for a system of n particles. Now, this problem 58 that I've assigned you is about the continuous extension of this idea to a distribution of mass in a one-dimensional sense. So you have something like, I don't know, you could think about it as just some sort of maybe like stick that has some kind of variable width or something. And then you could ask, okay, so like, where's the center of mass of such a thing like this? And what you can do is, building off the finite case, you can sort of think infinitesimally and say, well, I'm just going to chop that up into a bunch of little pieces. The little pieces would, say, have thickness dx. And you could ask, well, what's the dm here? What's the little bit of mass from that? Well, we define something called mass density. Lambda would be dm dx. So it's the mass per unit length. So in terms of lambda, which is called f of x in your problem, this little bit of mass would have something like dm is lambda dx. So that's how you get a little bit of mass. Now, so then, of course, you can kind of look at it as, what if n goes to infinity in the finite case? You can see it in that way. So in view of that limiting idea, as n goes to infinity, this sum becomes a Riemann sum, and the total mass, of course, is just the integral of dm over the object. Now, this is an intuitive expression I just wrote. How do you actually calculate such a thing? Well, then you need the details. So maybe this goes from, say, x equals to a over here to x equals to b, right? And so this would actually, the way we do this is the integral from a to b of lambda dx. Now, so that's how you'd find the total mass. That's part A. For your problem, that means to find the total mass, what you do is you integrate natural log of x from 2 to 3. That's why it's in the integration by parts section, because we know how to integrate natural log by integration by parts. All right, great. The next question, of course, is what happens to this guy? The continuous version of the center of mass formula for one dimension, x bar, the coordinates of the center of mass, will be 1 over m, where m is defined by that integral. All right, and then we have to do the integral of x dm over the object. Now that's, of course, this is a mnemonic. Well, it's an intuitive expression. What are the actual nuts and bolts of that calculation? How do you actually do it? How do you put it into practice? How do you calculate it? You do 1 over m, the integral from a to b of x lambda times dx, where lambda is the mass per unit length. And that, folks, is the formula for the center of mass of a one-dimensional object with mass density lambda extended from a to b. By the way, if the lambda is a constant, then this gives you what's called the centroid, which is the geometric middle of the shape. I mean, nobody asks you what's the centroid of a one-dimensional object, though, because it's like, it's really kind of a boring question. Like, what's the centroid of an interval from 3 to 4? It's 3.5, yeah. It's more exciting, though, this kind of question, because, you know, you could have something like some sort of tapered needle or something, and you could ask, what's the center of mass of that? That has interesting physical implications, because wherever it is, maybe here, I don't know. Well, there's a couple ways you could look at it. Now, one of the earlier section students was trying to solve this problem by saying that the center of mass should be where this mass and this mass, oh, sorry, I feel, and this mass are equal, right? Like that would be where the center of mass is, and they were actually trying to do the integral from like 2 to c and set it equal to the integral from c to 3. But if you've tried this, you get this algebraic expression, which is like x times natural log of x to solve, which we can't solve with elementary functions. So it's kind of, that was a neat approach, I thought. But it is the point where you have an equal amount of mass to the left and to the right of the center of mass. So it's actually where the thing would balance. So there's lots of interesting physical things about this center of mass. But that's how you calculate it, just that. Next question. Somebody else last class asked about the reduction formula. Like, what's the reduction formula? In problem 73. Yeah. So I did it for, here's the reduction formula carried out for n equals to 2. The reduction formula is actually given to you in problem 67. Problem 67, we're asked to prove this formula for n, and that can be proved by basically just an application of integration by parts. And once you have that, you can kind of bootstrap your way back from the top to the bottom. So like applying the reduction formula for n equals to 2, I have x squared e to the x minus twice the integral of x to the 2 minus 1, which is 1, e to the x dx. And then you can apply the reduction formula again to get this, and then out pops the answer. So for the problem that is in your homework, you just have to do this one more step, like x cubed. So you have to apply this 1, 2, 3 times in order to get the answer. But there are reduction formulas for sine, for cosine. There's one for natural log. That's problem 68. I don't talk too much about them in here, but they are there. And they may be faster than the way I teach you certain problems. I wouldn't deny it. Any questions? Other questions? Sorry, I haven't posted the solution to homework 1 yet. I fell asleep yesterday before I got a chance to do it. But as soon as I get a chance after class, I will post it. All right? So. 8.4?
Yeah, like the trig substitution.
Oh, no. Most of the rest of today we're talking about trig and hyperbolic substitutions. So you are correct. We are not done with that. I just was taking a couple of minutes to ask if you had questions about integrals of trig functions or integration by parts. Yes? Oh, yes. Thank you. And plus 2, right? You know, as usual, why has no one said anything in the earlier section about this? I mean, Well, if they have substantially lower test scores than you guys, I'll understand why. That'll make sense. I mean, maybe 815 is too early to do calculus 2. I don't know. Goodness gracious. Come on, people. All right, well, maybe I should leave everything I do in the earlier section up and just let you guys tell me what's wrong with it. Yeah. Other questions? Or corrections? All right, well, let's get back into the trig substitution then. So, if you draw your attention over here for a bit, what I have is the big synopsis of different substitutions that we can make, implicit substitutions. So yesterday, we actually carried out one that was based on this upper block right here, right? We talked about if you make a sine theta, x equals sine theta substitution, we could remove the radical with like the square root of 1 minus x squared, right? We use that to calculate the area of a circle as well. So this is one of the fundamental ones. If you've got a pattern like a squared minus x squared, you can set x equals to a sine theta. That will change this difference of squares to just one square, which is nice. But of course I have other identities, right? I've got like 1 plus tangent squared is secant squared, right? So if I let x equals to r tangent theta, then I have r squared plus x squared is r secant squared theta. So I change a sum of squares to a square, which is nice. Here's the triangle which organizes the relation between the angle and the substitution, right? This is nice because once you write this triangle in view of like for example, this substitution, what would tangent theta be? If we're working with this substitution, tangent theta is what? X over what? Great, yeah. All right, and then there's also a tangent substitution. I don't think I did one of these for you guys yet, but I will today, hopefully. And if we get a tangent substitution, we get a sum of squares becomes a square. There's also a secant substitution. A secant substitution takes x squared minus r squared and makes it into a square. So we have the pattern number minus x squared minus a number, and x squared plus a number. Every one of these sorts of patterns can be reduced, simplified with a trigonometric substitution. And in this way, we can eliminate radicals. But there's more. There is a world of hyperbolic substitutions in the same way. See, because hyperbolic functions also have wonderful simple identities, like cos squared minus sin squared is 1, or 1 minus tangent squared is hyperbolic secant squared, or cos squared minus 1 is you can read it. Hyperbolic cosecant squared. And each one of these identities also motivates a corresponding hyperbolic substitution. For example, since cos squared is 1 plus sin squared, if I make an x equals a sin phi substitution, then I have a squared plus x squared is a cos squared phi. So the meaning of the blue underline is I'm pointing out that this substitution is in competition with the tangent substitution. These both deal with something like a sum of squares. So to deal with a sum of squares, I can either use a hyperbolic sine substitution, or I could use a tangent substitution. Either one has a chance to make the problem easier. Also, if I let x equal tanh, that gives me r squared minus x squared is our hyperbolic secant squared, which is pretty nice as well. So you notice on the hyperbolic side we have sum of squares, number squared minus x squared minus number. So there's a duality here. I could either go with a hyperbolic substitution, or I could go with a trigonometric substitution for a given problem. You're like, well, wait a minute, but so you're telling me that trigonometric substitutions cover all the patterns? So you don't need to teach hyperbolic substitution, right? Because trigonometric substitution does everything already. So why bother with hyperbolic substitutions, right? Let me show you why. After we get through this pair of examples, I'm going to put away the projector and we'll work them out by hand. It's just this one I want to show you because it's kind of a pain to write out. And I also want to draw your attention to the fact that there is this thing called Chapter 9 in my notes, and it has many nice examples that are in addition to the book, and it has discussion of the hyperbolic substitution, which you won't find in the book. So you would be wise to look at my notes a little bit on this topic, of course. You can do it. You can do it. Ah, yes. I've given it the confidence. Woohoo! All right, so here's a problem. Integral of 4x squared plus 9 dx. Well, this one's a little bit of an annoyance because it doesn't quite fit the pattern of my table either. So this one we have to be a little bit creative. All right? So I already know what you guys are going to have questions about. Let me turn the lights back on. Just do it real slow and... yowzers. Try to explain what's going on over here. A little bit more detail. So we're faced with the square root of 4x squared plus 9, right? This we wish to simplify through some substitution. Now, I'm going to use the trigonometric root. The trigonometric substitution, the thing that involves the sum of squares, is 1 plus tangent squared theta is equal to secant squared theta. Right? This I know. To make this look more like what we're facing, what do? If I multiply this identity by 9, see what I have? Let me rewrite this. This is 9 tangent squared theta plus 9 is equal to 9 secant squared theta. Right? But what do I want? I want this to be 4x squared plus 9. That's my creative leap. So what that means then is I need this 4x squared to match this 9 tangent squared. What does that say then? What should I make? I should say 2x is equal to what? 3 tangent theta. That's where the substitution's coming from. I know that if I do what's in the purple, then what? That implies the square root of 4x squared plus 9 is just equal to the square root of 9 secant squared theta, aka 3 secant theta. Any questions about that? So, how many people in here haven't seen The Force Awakens? All right, now, is this for financial, ethical, or cultural reasons? Financial? Okay, I can respect that. It was expensive. I mean, I've only seen it, and my daughter, the rest of them haven't seen it yet, because I'm not going to take a 2-year-old to a 2-hour and 20-minute movie to watch him run around. I can do that at home. Also, it makes a better argument for why I need a 70-inch TV at home. You know, it's not right to watch the Star Wars Force Awakens on a 40-inch TV. It's not right. We need a larger TV. My wife says I'm abusing this word need, but I don't know. So you guys, you have no plans. Those of you who haven't watched it, you have no plans this semester to watch it. You're like waiting for Redbox, or just don't care about Star Wars because Star Wars is for nerds. Oh, that's also, okay, all right. There's no hope for you watching Star Wars Force Awakens this semester? If I made it a homework, would that do it? Like if I said, give me a report on, never watched it? No. If it was a homework, you'd watch it? Should, well, I guess we could watch it in class, but there's certain ethical, anyway, yes?
Can you just explain that again? Going from...
Our goal is to simplify the square root of 4x squared plus 9, right? So you mean going from here to here? So we just have arranged for 4x squared to be the same as 9 tangent squared theta, right? If you square 2x times 2x is 4x squared, but 3 times tangent theta squared is 9 tangent squared theta. See, so 4x squared is 9 tangent squared theta, but 9 tangent squared theta plus 9 is 9 secant squared theta. So it's really all about this 1 plus tangent squared equals secant squared theta being manipulated. This is
So
the...
that is the substitution that we would use.
The substitution is built over this identity. 1 plus tangent squared equals secant squared theta. But yes, 2x equals to 3 tangent theta is the actual substitution we're going to make. Absolutely, yeah. Let's do it over here. So with that understood, 2x equals 3 tangent theta, this square root of 4x squared becomes the square root of 9 secant squared theta. And dx, well, dx is the derivative of tangent. It's 3 secant squared theta and divide by 2 because I get 2 dx over there, you know. Everybody with me here? All right. Follow along. Next, we get ourselves a 9 halves because 3 times 3 is 9 and 2. And then, oh no, the dreaded secant cubed. This is an unhappy place. We went there yesterday, remember? There was an integral of secant. The thing looped back on itself after an integration by parts. It wasn't that much fun. I mean, I think it was fun, but some people would say it wasn't fun. Anyway, this is not an easy integral, but we did it yesterday, and here's the answer. Now, after that's done, you have to undo this using ye olde triangle. So, of course, tangent theta is 2x over 3. And what's secant theta for this triangle? Hypotenuse, right? Over adjacent side, which is 3. Okay, so all of this exploding box. There, now it's exploding. See? This exploding box is connected to this example, all right? You see what I did? So secant tangent is square root of 4x plus 9 over 3 times 2x over 3. The 3 and 3 gives me a 9. That 9 cancels this 9. 2 times 2 is 4. So there's the, 2 over 4 is 1/2. So there's the secant tangent term. And then over here, you have this. We can simplify that. You notice if you've got 1/3 on both things, let me just show you what's going on there. If we have the natural log of stuff over 3, it's the same as the natural log of stuff minus the natural log of 3, right? So if you have a common denominator inside a natural log, you can simplify that by just pulling out a minus natural log of 3. But the thing is, we're integrating, right? So we can just throw this minus natural log of 3 into the constant of integration without loss of generality. And so here's a good answer. 1/2 x squared root of x 4x squared plus 9. 9/4 the natural log of the square root of 4x plus 9 plus 2x plus a constant. Yes, sir?
Are we going to have to like do the integral of secant cubed, or now that we know it, we can just say it's...
For homework, you can just reference the day of class that we did it. Now, if the whole question was integrate secant cubed, then I'd want you to work it out. If it's part of a larger question, you can reference earlier work, yeah. I mean, like I said yesterday, integral of secant cubed is not something I expect you to have memorized. So if there was a problem on the test where you came to an integral of secant cubed, I probably expect you to work it out. Because like I said, I haven't expect you to memorize it, you know. That would be an epic test question, though. This is unpleasant, yes? But maybe the point of the test question is that you shouldn't do this. Maybe the point of the test question is that you should do what's following. See, because if we adopt a hyperbolic substitution, right? So which hyperbolic substitution gets 1 plus something squared? That's this one. See, if I let a equals sinh, then I get a squared plus x squared is a cos squared, you know. So a hyperbolic substitution, what I'm going to do is let 2x equals 3 sinh theta. If I let 2x equals 3 sinh theta, that means that 4x squared is 9 sinh squared. Phi, not theta, sorry. So 2x squared equals to 3 sinh phi means that 4x squared plus 9 is 9 sinh squared phi plus 9, but sinh squared plus 1 is cos squared, so we get 9 cos squared phi. And if we differentiate the substitution, we also get 2 dx is 3 cos phi d phi. So the hyperbolic substitution gets us this. Square root of 9 cos squared phi, 3 cos phi d phi over 2. You pull out a 9 halves, and you got yourself an integral of cos squared. Cos squared is an easy thing to integrate. Oh, that's because my substitution, I'm going to erase this stuff here. We don't need more. So now the substitution was 2x is equal to 3 sinh phi, right? And so 2 dx is equal to 3 cos phi d phi. So dx is 3 halves cos phi d phi. So that's where the half is coming from. It's from the substitution. So that the half is part of the dx. Yes, sir?
So do we have to remember this table? Right.
Probably. I mean, I'd like you to understand it as opposed to remember it. But yeah, I mean, essentially, to understand this section, you understand this table. But it's not just that, right? It's how to use the table as well. But that you start seeing a few examples, it will start to click, I hope. So like this one here, the trigonometric substitution went badly. So we might try a hyperbolic substitution. Hyperbolic substitution, on the other hand, gives me cos squared phi d phi, which isn't bad because if you go back to the definition of cos, that's 1/2, sum of the exponentials, and I can just square that thing out, and I can derive this identity right quick, right? Cos squared phi is 1/2 cos 2 phi plus 1/2. If you forgot that, you could easily derive it, right? Just like I did from scratch right here. Yes, sir?
This is the same identity as normal trigonometry function, so can we just use it?
Not always, though. Which ones are different? Most of them are the same, but there's something somewhere.
The sign comes when you
The cosh of a plus b as a plus rather than a minus comes to mind. The tanh adding formula has a different sign in it. I have not taken the time to systematically list where the analogy breaks down. So I can't.
And if it's the same, can we just use it, or we have to derive it?
Oh, if you already know that cos squared phi is 1/2 cos 2 phi plus 1/2, you can just use that. Yeah, sure. Just make sure that you don't remember it wrong. But once we have that, then we can integrate this, right? 1/2 of 1/2 sinh 2 phi, and that just integrates to phi, but we got the 9/4, so we get 9/8 sinh 2 phi, 9/4 phi. Now what I did earlier was like, okay, so in order to derive, I need an identity for sinh 2 phi to kind of make this answer pretty. So what I did was I took the Well, let you guys catch up before I'll pause for a minute here, make sure you're all with me. See, because I'd really like to tell you that story about like my daughter and what she said at the Christmas dinner, but I can't in good conscience with those of you in here who have not watched the movie. I mean, it wouldn't be right. You don't care? Maybe I should take a time and be like, all right, everybody who doesn't want the movie to be spoiled, leave the room. And then I'll tell you what was said. Maybe we'll do it at the end of class today. How about that? Yeah. All right, yeah. Are you guys with me so far? All right, so we got to here. Now, we want to put our answer as an algebraic expression to have the best answer. So I need to simplify sinh of 2 phi. A nice way to derive that, like if you already know the cosh 2 phi identity, if you solve for cosh 2 phi, we get this. You guys agree with me? So just take what I derived here and solve for cosh 2 phi. You get cosh phi is twice the cosh squared minus 1. That's nice, though, because if you just differentiate this identity with respect to phi, out pops the sinh 2 phi identity. See this? Derivative. Cosh goes to sinh. Chain rule gives me a 2. Chain rule over here for the square function gives me a 2, and then this. You divide by 2, and there you go. Sinh 2 phi is 2 cosh phi sinh phi. At which point, the gentleman in the front will say, that's the same as the trigonometric identity. Can't I just remember that? Yes. I don't deny you that. I'm just showing you how you could derive it if you forgot. So you can squish the purple calculation to a thing you know if you want. It's your prerogative. All right, so sinh 2 phi is 2 cosh phi sinh phi. All right? And it was pointed out to me earlier. Now, this is not in my notes, but it's something new the earlier section added. This was a student's idea, is that we could draw similar triangles based on the hyperbolic substitutions in the same way we draw triangles for the trigonometric substitution. I think one of you was trying to get me to do this yesterday too as well, right? Somebody here asked that? No, not quite. Well, but the rub is it's a little sneaky. Like, so here would be sort of the basic thing you'd think about. If I put cosh as the adjacent side, if I put sinh as the opposite side, the thing is cosh squared minus sinh squared is 1. So if this is a and this is b, what has to be up here is a squared minus b squared. Well, square root of that, really. So we thought about it, and I thought, well, if it works for cosh and sinh, then it should be generalized. And so here's like the general hyperbolic triangle. If I have side A, B, C, they're related in this way. A is the square root of b squared plus c squared. B is the square root of a squared minus c squared. C is the square root of a squared minus b squared. These are all bound together by this identity, a squared minus b squared is equal to c squared. So these are the rules for generating sides of the hyperbolic triangle one from another. For example, in this problem, we have the triangle 2x, like this is what we're given, right? Sinh of 2 phi. Sinh of phi is 2x over 3. So I can do what? I can go, this is like the what? This is the opposite over the hypotenuse. And so that, if you follow the blue snake, goes down to here. Let me make a red thought bubble. You can ignore the red thought bubble for a moment. Okay. I add the sound effects for free. Now, so this green triangle, you got the opposite side is 2x, the adjacent side, the hypotenuse is 3, right? Then the rule is to get the other side, I do the square root of b squared plus c squared. So I do the square root of that squared plus that squared, but that's 4x squared plus 9. So the missing side will be the thing we're trying to eliminate, just like with the trigonometric triangles. So these little mnemonic triangles to remember the relation between cosh sinh and tanh for the hyperbolic substitution. They play the same role as the triangles do for the trigonometric substitution. The rub is the relation between the sides is complicated because, well, it's different because a squared minus b squared is equal to c squared instead of a squared plus b squared equal to c squared. But otherwise, it is a useful mnemonic to remember the relation between the hyperbolic functions and the sides. If you don't like the triangle, right, you could also work straight algebra. You could start with cos squared minus sin squared equals to 1, and you could plug in that sinh was 2x over 3 and solve for cos phi and get the same thing. See how you get from here? This triangle tells me what? Cos phi is what? I do adjacent over hypotenuse, right? Which is the square root of 4x squared plus 9 divided by 3. As you can see, what's in the red thought bubble, this can also be derived by algebra alone. But the triangle is a nice way of doing it. I drew the triangles for the hyperbolic substitutions in each one of these. Like for sinh, it's like this, ax, here's the square root of a squared plus x squared. For this one, for tanh, you got x here, you got r here, you got square root of r squared minus x squared. For the coth, you've got r here, you got x here, you got square root of x squared minus r squared. What's in the square root is the thing we're trying, the thing you have to add to the triangle is always the thing we're trying to simplify with the substitution. So, in view of that, I can take the sinh2 phi and I simplify it to sinh cosh, which is 2x over 3, square root of 4x squared plus 9 over 3. And you do some arithmetic, the 9's cancel, the 2 and over 4 gives you a half. We get 1/2 x times the square root of 4x squared plus 9. And then this phi, we can solve. I mean, if you solve this for x, what do you get? Solve for phi, rather. This tells me sinh phi is what? 2x over 3. So phi is inverse hyperbolic sine of 2x over 3. So that's where that is coming from, right here. See, this is that. Both of these examples are hard to you guys right now because you're just at the start of learning this. So they both probably seem impossible to you at the moment. That's okay. You need to do homework. The homework makes impossible things seem possible, right? Let me just preach to you a little bit. This is way easier than this. I hid the difficulty of, the difficulty of going from here to here is substantial. Everything I did in the hyperbolic substitution, not that hard, really. Now, but it's fun to compare the answers, right? We've got two rather different answers. For the trig substitution, we ended up with a natural log of the absolute value of square root of 4x squared plus 9 plus 2x, and this function out front. We got the same function out front here. Check it out, right? 1/2 x times root, 1/2 x times the root. Right? Matches. But then you got this versus that. But those are the same thing. Remember, the inverse hyperbolic sine can be written as a natural log of an algebraic function. So you go back to that theorem 7.9.2 back in section 7.9, and these are actually the same answer, just written in a different notation, which I find fascinating. But then again, I'm easily amused. Let's see here. All right, so any questions about this? I want to put it away and work some examples for you guys by hand. Yeah.
What happened to the natural log of 3 in the first example?
The division by 3? I lumped it into the constant. So I've got division by 3 both places, so I can say that this is really the root plus 2x divided by 3. But then, since if I have stuff divided by 3, it's the natural log of stuff minus the natural log of 3, I can throw the minus natural log of 3 into the c. So technically speaking, this c and that c are different. Yeah. But this is our custom, is to abuse the symbol c in these kinds of things. This abuse is also rampant in differential equations. Other questions? All right, let me put this away. Again, this is my chapter 9. I would encourage you to look through it. My notes are not universally helpful in this course, but in certain places they really are. This is one of those places. All right. Let me jump off a cliff here and see what happens. Integral of x over x squared plus 9x plus, I don't know, 13. You're like, there's no radical. Yeah. I guess I don't need one. Fine, I'll put one in. I'll make this a minus. Make this a minus and put a square root. See what that does to us. All right. This one actually is not quite the same as the ones we've looked at, because this involves an extra step. That extra step is called completing the square. Oh, no. No, 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 no. That is an 8. That is definitely an 8. That is definitely an 8, and this is definitely a plus 12. Wait, do I want minus 12? Just a second here, guys. Don't look. All right. I don't have to explain this part to you, because one of the things I don't require you to do in this course is make up problems. Right? So there you go. So that's x plus 4 squared. Now let me explain what I'm doing. The whole goal of completing the square is to lump all of the variables into a square. And we're talking about a quadratic expression. So x plus 4 squared is what? Right. So you see I have to do what? This is plus 7 minus 16. To be fair. If I add 16, I have to take it away. And that, folks, is completing the square. So what I have here, right, is the integral of x dx over the square root of x plus 4 squared. What is it, minus 9? Yeah, minus 3 squared, right. All right, so now it's kind of the same pattern as we have over here, right? It's a difference of squares at least. So there are two ways we could go here. We could do what? Yeah, we could make a secant substitution, or we could try a coth. I'm going to go with secant. I don't feel like working stuff out with coth at the moment. I think we can make secant work. So let's try it out. So so here's the deal. We're going to let x plus 4 equal to 3 secant theta, because I know if I do that, I'm going to have what? I'm going to have x plus 4 quantity squared minus 9 is equal to what? It's going to be equal to 9 secant squared theta minus 9, aka 9 tangent squared theta. Which is really nice because that simplifies the denominator considerably. What's the dx? Yeah, dx is 3 secant theta tangent theta d theta. All right. There we go. There's our trigonometric substitution thought bubble. And what does it get us? Hopefully something fun to integrate. Let's see here. We get x times 3 secant theta tangent theta d theta divided by the square root of 9 tangent squared theta. Yes, sir.
Shouldn't we make x equal to 3 secant theta minus 4?
Can't we just ignore x? You shouldn't. Don't let me bully you. That was a nonsense question. I mean, I'm doing this on purpose. I want to draw your attention to the fact that no, in fact, I can't just ignore x, right? I mean, we have to change x to theta as well, right? This is a common mistake I see in tests. People just like, oh, there's an x there. I don't know what to do with it. I'm just going to just leave it there. Pretend like it's not there. This does not impress me. I look very dimly upon this when I grade. Just saying. You must deal with the problem you're given. So anyway, this tangent, right, cancels. It's like this and that cancel. This and that cancel because square root of 9 is 3. And we're just left with the integral of x secant theta. But what is x? I'll tell you one more step, x secant theta. What is x? X is equal to, you're about to tell me 3 secant theta minus 4, is that right? All right. So what we have then is 3 secant theta minus 4 secant theta d theta. Now, I think you see why, maybe you're starting to understand why I said we needed to know the integral of secant theta. We want to just have it memorized, right? Because you see it's coming up. I mean, look at the original problem here. Does that look like a secant theta problem to you? I mean, I look at x dx over the square root of x squared plus 8x plus 7. I go, man, I sure hope I know the integral of secant theta. No, you don't think that, right? It's hidden. But it's lurking. There it is. This is what? This is secant squared theta? Yeah? Oh, that's cool. Huh. Minus 4 natural log of the absolute value, secant theta plus tangent theta. That's the integral of secant. Plus what? Yeah. Right, that's an elementary integral. Now we're not content with that. We want to simplify this. We use the triangle. Theta. What was my substitution? Secant theta is x plus 4 divided by 3. That makes the hypotenuse x plus 4. It makes the adjacent side 3. And the other thing is the thing we eliminated, square root of x plus 4, quantity squared minus 9. Of course, you could write this instead as what we had to start with, which was x squared plus 8x plus 7. Okay, so in view of the triangle, what does the integral actually look like? Minus 4 natural log of the absolute value of x plus 4 over 3 plus tangent theta, which is what? Plus the square root of x squared plus 8x plus 7 divided by 3, close absolute value, plus thrice the tangent of theta. Tangent theta was square root of x squared plus 8x plus 7 divided by 3. All right, all of this plus a constant. Now, yet again, my natural log of stuff divided by 3 comment applies. See, because I have division by 3 both, I can clean this up just a bit. This is really minus 4 natural log of the absolute value of x plus 4 plus the square root of the x squared plus 8x plus 7 close absolute value plus the square root function 8x plus 7, x squared plus 8x plus 7. And then plus some other constant, let's say. I'll tell you what, I won't abuse the constant. This time I'll call it C2. Here C2 is what? C2 is C minus 4 times the natural log of 3. Plus 4 natural log of 3, actually. And that, folks, is about the best answer I can give you, so I'm going to stop right there for this example. Yes, sir.
I missed your reasoning on the
Well, so here, right, this expression is really x plus 4 plus the square root of x squared plus 8x plus 7, all divided by 3, right? So if I take the natural log of this, it's the same as the natural log of x plus 4 plus the square root of x squared plus 8x plus 7 minus the natural log of 3 by properties of log. But I got a minus 4 out here, so I get plus 4 natural log of 3 added to the constant, and I can just call all of that C2 for the final answer. I don't know. Like I said, I want you to write the answer which best reflects your understanding of the material as deeply as you can. So, I have a doctrine of grace. I don't want to force you into some sort of legalism. But on the other hand, I want you to do what's best. So, like, you're being ambiguous. Yes, I know. Let's go on. Other questions? Yes? Yeah?
Do you know like when a problem is to use the trigonometric substitution?
No. I don't know. I don't have some. I have not studied enough examples to give you an overarching advice to that answer to that question. I mean, my current MO is just to try one, and if I find myself facing a secant cubed, try another one. But usually, I would start with trig substitution since I'm more comfortable with it personally. But here's another example. How about this? Integral of 1 over x squared plus 4x plus 5 to the 3/2 power dx. So this is another one of these completing the square ones, right? So let's complete the square. It's not too bad in this one. So this example is pretty nice, actually. This is x plus 1 squared. Oh, plus 2, right? Plus 1 all to the 3/2 power. Let's see here. So I can, I mean, of course, I can make a u substitution if you want. I won't do that, though. I'll just go straight and say, okay, so what's the trig substitution you want to do here? Yeah, we face the sum of squares, so we should make a tangent theta substitution if we're going to use trig substitution. And do I need any number? I don't think I do. I got a 1 here, which is really nice, right? So I don't even need to do some kind of like multiple like we did in the previous one. So x plus 2 quantity squared plus 1 is equal to tangent squared theta plus 1, which, by the way, is secant squared theta. We also have that dx is secant squared theta d theta. So there's my trig substitution thought bubble. So what have we got? We've got ourselves secant squared theta d theta divided by secant squared theta to the 3/2, yeah? What is secant squared to the 3/2 power? Secant cubed, right? Like, oh man, secant squared over secant cubed, that seems impossible, right? Oh no, it's 1 over secant. If secant's hard, can you imagine how hard 1 over secant must be? Oh man, well, there's no hope for us. There's just no hope. Until you realize that that's what? It's cosine. Sorry, it's kind of anticlimactic. There you go. Which has integral of what? I think this one you can do. Sine plus a constant. And what is that sine theta? Theta. What's my substitution? Tangent theta is x plus 2 over 1. Use your imagination to see the 1 there. So it's x plus 2. Adjacent side is 1. Over here, we have the square root of x squared plus 4x plus 5. And so sine theta is what?